Okay, so the workbook has been hinting for dozens of pages that there's something a little off with the way we've been writing our chemical reactions, and now we finally get to fix it. The issue is this. When you write a reaction and you say that you're starting off with a certain number of atoms, when the reaction is over, you should be able to account for every one of those atoms that was there before. So in this reaction, for example, we start with two nitrogen atoms, and afterwards we only have one. That's a disaster. That's just as bad as losing money in accounting. If it happens, you immediately start trying to figure out what went wrong. And so we need to fix these reactions so that however many atoms you began with, you end up with the same number. It is also a problem that this reaction starts with two hydrogen atoms, and at the end we have three. So let's deal with that. The way we can deal with that is we are allowed to put numbers in any of these spots. These numbers sit out front of the formulae. They are called coefficients, just like in math. We can put any number we want in those spots. We can't change these subscripts. So like writing H3 here would fix the hydrogen problem. Not allowed to do that. The only place you can put multipliers are in those boxes. So what do we put? Well, for starters, this reaction begins with two nitrogen atoms. If we put a 2 here, now we have two nitrogens on the right. We have 2 times N and 2 times H3. So that's good. That means we have two nitrogen before and two nitrogen after. That's the beginning of something good. But now on the right, we have 2 times 3. We have 6 hydrogen on the right. So we need to have 6 hydrogen on the left. Could we do that? Yep. We can put a 3 right there. And now we say this thing is balanced. We started with two nitrogens. We end up with two nitrogens. We started with 3 times 2 is 6 hydrogen, and we ended up with 2 times 3 is 6 hydrogen. So all is good. You can leave this space blank if you want to, or you can put a 1 in there if you want. And in fact, if we asked you for the coefficients of this balanced reaction, which they sometimes do, you would have to say the coefficients are 1, 3, and 2. Okay, let's try lots more of those and see if we can get comfortable. H2 and CO reacts to CH3OH. So, counting atoms here, we have 2 hydrogens on the left, and on the right we have 3 hydrogens, and 1 more here makes 4. We have a single carbon, and over here a single carbon, and we have a single oxygen, and we go to a single oxygen. So really, everything here is fine except the hydrogen. Right now our hydrogens, we have 4 on the right and only 2 on the left. If we double our amount of hydrogen, that's actually all we need to do. Now we have 2 times 2 is 4 hydrogen. Over here, 3 hydrogens plus another one makes 4. 1 carbon, 1 carbon, 1 oxygen, 1 oxygen. So that went fairly smoothly. If you want, again, you can put a 1 there and a 1 there to make it all complete. And that's that one balanced. This is hydrogen burning an oxygen to produce water. What do we need here? The hydrogen's actually good. We have 2 hydrogen and 2 hydrogen, but we started with 2 oxygens, and this is only showing a single one. So what happens here is, because we have 2 oxygens here, we have to double the right-hand side. What's good about that? We started with 2 oxygens, and now we have 2 oxygens at the end. What's bad about that? We just broke our hydrogen. We have 2 times 2 is 4 hydrogens on the right side now. We need 4 hydrogens on the left, which means now we need a 2 there. And that's done. Throw in a 1 here if you like. Okay, so sometimes in the process of fixing one element, you break another one, and then you have to go fix that. And it can feel a bit like you're running in circles, but there's almost always a way that you can get everything balanced at once. Just be patient and fix one thing at a time, and usually they will work out in the end. Okay, now they go a bit horrible on us. Good news with these, when you have a polyatomic ion, you can think of it as a single unit. You don't necessarily have to count N's and O's when you're doing an ion like this. You can think of this as just, I have a single nitrate, and over here I have two nitrates. Instead of counting N's and O's individually, you count this entire thing as a clump. So if we were trying to balance this, well, let's get right into this. We have a single nitrate here, but we have two nitrates on the right. So I need to double the amount of nitrate on the left side. That means putting a 2 there. But that's a problem because now I have 2 silver on the left and only 1 on the right. So I'll fix that next. If I put 2 silver here, that takes care of the silver problem. But now I have 2 chlorines on the right, and oh, there's already 2 chlorines on the left, so that part's okay. And for calcium, we have 1 calcium and 1, so that's all good. That's all good as well. So this thing's balanced with blank 2, or if you'd rather, you can put 1s in those blanks. Checking again really fast. 1 calcium, yep. 2 chlorines, yep. This 2 applies to the chlorine. 2 silver, yep, that 2 applies to the silver. And 2 nitrates, yep. This 2 right there says that there are 2 nitrates on the right. So, all good. What do we do with this thing? Phosphorus meets chlorine and produces phosphorus trichloride. Well, the obvious problem is we have 4 phosphorus on the left and only 1 on the right. So if we do this, now we have 4 phosphorus before and 4 phosphorus after. That's good. But now, how much chlorine do we have? 4 times 3, we have 12 chlorine on the right. Only 2 over here. How do you solve that? Well, what times 2 makes 12? Ta-da! So now we have 4 phosphorus and 4 phosphorus here. The 4 affects the P. Here we have 6 times 2 is 12 chlorine, and here we have 4 times 3 is 12 chlorine. So all is well. And again, you can put a 1 on the phosphorus if you like. Okay, what's happening here? 1 calcium, 1 calcium, 1 carbon, 1 carbon, and here we have 3 oxygens. Here there's an oxygen, and here there are 2 more, total of 3. So they say sometimes this happens. Some reactions you don't have to change anything. Some reactions are balanced as written, and that's wonderful when it happens. You don't have to do anything here. You can put 1s in all these spots if you like, but that's it. No need to change anything. It isn't real common, but it sure is nice when it happens. Now, this is the first one we've seen that is a hydrocarbon combustion, and these can be a little strenuous if you don't do them the right way. The main advice I would give you for these is do the oxygen last, and I'll just dive into it, and I'll show you in a moment why it's helpful to do the oxygen last. Let's go with that. We start with 3 carbons, so we need 3 carbons on the right side. Take care of that by putting a 3 there. We start with 8 hydrogen, so we have to have 8 hydrogen when we're done. We could arrange that by putting a 4 here. That'll quadruple the amount of water. Now, the reason we waited on the oxygen is counting up the oxygen on the right side is a little complicated, and a lot of people fumble here. So take this nice and slow. We have 3 times 2 makes 6 oxygen. And over here in the water, we have 4 times 1 is another 4 oxygen, and 6 plus 4 together means we have 10 oxygens on the right. To balance that out, we need 10 oxygens on the left, which means 5 times 2. Fair enough? If you try to do the oxygen earlier, it's very tricky to do because you don't have, then you'll fix the carbon or you'll fix the hydrogen and the amount of oxygen will change again and you end up kind of chasing your tail. much smoother if you put off the oxygen until the end because it's the most complicated part. The carbon will kind of force your hand as to what number goes here. The hydrogen will tell you what number goes here, and once these are both resolved, then it's time to worry about the oxygen, but not before. So remember, oxygen's coming from two different places. Just take your time, do them each carefully. You should be fine. What have we got here? This has a polyatomic in it. We have aluminum metal, reacts with hydrogen sulfate. This SO4 is sulfate. Then we get aluminum, and here's sulfate again. And then we get hydrogen gas. So if we're counting, where do you think we should start? Tell you what, I'm gonna start this one. I'm going to do something that might get me into trouble just because I want to see. And if it does get us into trouble, I'll show you how we deal with it. I see here we have one aluminum, and on the right side, two aluminum. So let's fix that and put a 2 there. Now, we have, or if we go left to right, let's do that. 2 hydrogen. We look over here and we see 2 hydrogens, so good, that's looking okay. Then we get to the sulfate. We have a sulfate here and 3 sulfates here. So we ended up with 3 sulfate. That to make that happen, I have to put a 3 on the left. But what happens now, how many hydrogens have we got? 3 times 2 is 6, which means I have to put a 3 over there. Okay, I thought that would cause more trouble than it did. Are we all okay here? 2 aluminum, 2 aluminum. 3 times 2 is 6 hydrogen. 3 times 2 is 6 hydrogen. 3 sulfates, and here 3 sulfates. Yeah, that's okay. I thought we might have to backtrack when we were doing this one, but it worked out okay. Maybe that'll happen in a later problem. We can put a 1 in that spot if we want to, and yeah, that worked out fine. Now, what have we got? Iron reacts with water, and we get Fe3O4 and hydrogen. Okay. How do we start this? For iron, we start with 1 and we end up with 3. So putting a 3 there seems reasonable enough. That takes care of the iron. Hydrogen, we have 2 and 2, so that's looking okay for now. Oxygen, we have just 1 on the left and 4 on the right. Well, that's no good. Have to put a 4 here. But now do you see what just happened? We thought our hydrogen was okay, but now we just broke it. We had oxygen 4 on the right. Putting a 4 here fixed the oxygen, but now we have 8 hydrogen on the left, meaning we need 8 hydrogen on the right. Need a 4 right there. So this is why you'll see I check these more than once before I pronounce them done, and this is why, because sometimes fixing one problem creates a new one, and you have to make sure before you're done that you've really got all of your elements balanced out. So a final check for this. 3 iron looks good. 4 times 2 is 8 hydrogen. 4 times 2 is 8 hydrogen, and 4 oxygen there matches 4 oxygen there. So yes, I think we're okay. As usual, 1 in the blank if you want to. And they finish with a big one. This is octane, or gasoline, and it's burning, and we get carbon dioxide and steam as usual. And they remind you to balance oxygen last, because you can tie yourself in knots if you don't. Something a little unusual happens with this one, and so let's just let it happen and then we'll figure it out. Carbon. There are 8 on the left, we need 8 on the right. Easy enough. Hydrogen, 18 on the left, so we need 18 on the right. What times 2 makes 18? The answer is 9. Now, careful, how much oxygen do we have on our right-hand side? 8 times 2, we have 16 oxygens in our CO2. 9 times 1, we have 9 more oxygens coming from our steam. 16 plus 9, we have 25 oxygens on the right-hand side. And this is where it gets a little bit weird. On the left, oxygens come 2 at a time. So we're thinking, what times 2 makes 25? And there are 2 ways people react to this. The first is to say, we're doomed. 2 doesn't go evenly into 25. We can't do this. And the other way is to say, well, if you do 25 divided by 2, the answer is 12.5. So that tells us 2 times 12.5 would do it. You could put a 12.5 there. Oh, not quite enough room. Pointier pen. 12.5. If you're not a fan of decimals, you could instead write the fraction 25 over 2. That's okay. So either one of those would balance this reaction. Now, some chemists don't mind if you put a fractional coefficient like this, and others say you shouldn't do this because there's no such thing as half an oxygen molecule. You either have an oxygen molecule or you have 2 or 3, but you shouldn't talk about pieces of them because those don't normally happen. I don't mind the decimals myself, but if you're working in an environment where you've been told not to use the fractions, it's not so bad. All you do is double all of these coefficients. You can go through the entire reaction and say, instead of 1 octane, I'll use 2. Instead of 12.5 oxygens, I'll use twice that much, 25. Instead of 8 carbon dioxides, I'll use twice that much, 16. And instead of 9 steams, I'll use twice that much, 18. Now all your coefficients are whole numbers, everybody's happy, and this reaction will still be balanced. So again, I don't think this is necessary, but if you ever are told that there shouldn't be fractions in here, no problem. Just double everything and it'll get you out of trouble.